So today we're going to do linear regression. And the first thing I want to talk about is a regression line. So actually, you might have guessed this based on previous lessons, but when we're working with a scatter plot, we like to predict the pattern, and we often do that by drawing a line through it. So what the regression line is it's a line that describes how x, your explanatory variable, and y, your response variable, are related. So the general equation of a regression line is y hat equals a plus bx. And the y hat is what we call our predicted value of the response variable. I'm just going to write predicted value. So the hat on top of the y means predicted. The a is our y-intercept. And I know in previous classes you've probably seen b as your y-intercept, but just remember the number by itself is the y-intercept, and in this case our b, which is the number with the x, is our slope. So our next example looks really long, but you actually have a lot more information than you need. So go ahead and read through it. And I want to point out that the equation should be soda, and the soda actually has a hat over it, but my word processing program didn't let it appear. So all we're doing for this thing is we are identifying the slope and the y-intercept of the regression line. I will show you later how to find this equation. We did the scatter plot in the previous section, so I don't want to spend a lot of time doing that right now. But all we're doing right now is we want to find the slope, we want to find the y-intercept, and we want to discuss what they mean in context. So first thing is, remember, my slope is the value with the x variable. In this case, you'll notice that my x variable is tapping time. So actually, this equation put that in there already. And my y variable is soda, which the equation also put in there. So my slope is going to be 2.63. My y-intercept is the value by itself, which means it is 248.6. So let's discuss what these mean based on stuff that you've learned in previous classes. So just a few definitions, I'm going to write them off on the side. The y-intercept is going to be the value of y when x equals 0. So it's the value of y when x equals 0. And in this case, our y-intercept is 248.6, so this is going to be the value of milliliters of soda when the tapping time is 0. So the way that we're going to word this is that if we were to tap this for 0 seconds, we would expect the amount of soda to be 248.6. So, or if you can even say if the soda can was not tapped at all, this would be our predicted value. So if tapping time was 0 seconds, we would predict that there were 248.6 milliliters of soda. So now let's talk about slope. Slope is a little bit harder. So slope, you might remember from previous classes as rise over run. And an easier way to think about it in this case is as change in y over change in x. So my slope here is 2.63 over 1. It's always going to be over 1, unless you already have it as a fraction. So the 2.63 is going to be my change in my y, which is soda, and the 1 is the change in the tapping time. And because it's positive, we're talking about an increase. So the way that you're going to word this is you're going to say something like, for each additional second that the can is tapped, the amount of soda increases, and remember we use the word increases because it's a positive slope, by 2.63 milliliters. And actually I missed an important word. I should say the predicted amount of soda. So for our next example, we are going to use the equation to predict the amount of soda remaining if the can has been tapped for 10 seconds. And I actually have written out the equation for you up there. This problem, thankfully, is actually very easy. So all you're going to do is, we know our tapping time is 10 seconds. We're finding the predicted amount of soda, so you can write it out as predicted soda equals 248.6 plus 2.63 times 10. Luckily in this class you can use your calculator 100% of the time, so you can just use it to find this. You'll find that the predicted amount of soda is 274.9. Do not forget your units, it's milliliters. And that's all that you need to do for that. So the next problem actually has an important vocab word in there, which I'll talk about in just a second. But the first thing I'm going to ask you is, why should we not predict how much soda will be left after 60 seconds of tapping? And I've pasted a picture of the plot on there so you can look at it. And the important thing that I want you to notice is that all of our tapping times down here that were tested were between 0 and 12 seconds. 60 is really, really, really far away from those. And this is what we call extrapolation. And it's extrapolation, I'm going to put an exclamation point. This is a very bad thing. I'll just write bad there just so you remember that. So what that means is that 60 seconds is far away from all the other data. We can't predict anything that far away. So it's too far away. You can just write out a sentence something like, since all of the tested times were between 0 and 12. We do not know if the same pattern would continue. And if that happens, I do want you to mention the word extrapolation. This would be extrapolation. And actually, if you want to think about this logically, if you were to check it for 60 seconds, you would get something more than a liter, which is much, much bigger than a can of soda. So it would be completely impossible to predict that. You would get an outrageous value that wouldn't work. So that's one example of why extrapolation wouldn't work. So we have one more thing to discuss today, and that is what we call the residual. So the residual is going to be the difference between your observed value of your y and your predicted value. And I'll explain what I mean in just a minute, but first I'm going to write the formula. So the formula is residual equals, you can either call it your actual, which I prefer, or your observed value, which also is fine, minus your predicted value. And this formula is really long. If you want to do it, write it like R equals A minus P and think of it as RAP. That's a good way to do it. That way you'll remember the order. So this is going to be very important. It tells you how far your line, the guess from your line, is from the things that you actually got. And let's do an example. So for this example, I've put a few things here for your reference. And we want to find and interpret the residual for the can that was tapped for 4 seconds and had 260 milliliters of soda remaining. So if you look at the original table that they gave you, it's this value right here. And on your graph, I'm going to try to highlight it in pink. It's going to be around there. It actually looks like it was very close to your original line, which means the residual is going to be very small. So this value here is actually going to be our actual or observed value, this one right here. So you can write it like that. The predicted value you're going to find by using your original regression equation. So what I'm going to do for my predicted is I am going to take that equation and substitute in 4 for my tapping time. When I do that, I end up getting 259.5. So this is what my equation predicts to be the value when I tap a can for 4 seconds. So then I'm going to put it all together and find my residual by doing 260 minus 259.19, which gives me a residual of 0.88. And actually, what that is that's the distance between the point and the line, which is really hard to see on here. I'll do an example in class where it's a little bit more clear. So what that means is that this can of soda had 0.88 milliliters more, because it's positive, it's going to be more, remaining than what we expected. And what we expected was what we had in our original equation. So this is our residual.